talk about. You're going to talk about helium-3 too.
I've changed the title. Kind of. Well, yeah. So should I explain what I did? Right.
Okay.
Yeah. Hello. Good afternoon. Yeah. Well, thanks to organizers for arranging the meeting in such a nice place. Yeah, I took liberty actually and tried to pack more material into the talk because I can see that people are interested in topology, and I think superfluid helium-3A, our experiments and sometimes simulations with that actually give you more kind of information about what can be done in superfluids. Quite a few people were involved at different stages in different experiments here, and also an instrumental part of this experiment is the rotating cryostat in Manchester, with which we can not only cool down helium to low temperatures to make it superfluid, but also can engage it into some flow, for example, steady rotation or some AC rotation. Yeah, there will be two subjects of this talk. One will be the superfluid helium-3A. It's a chiral P-wave phase of superfluid helium-3A, which exists below 2 millikelvin. And it's actually, even though it's at very low temperatures, the limit is high temperatures. It's immersed into viscous normal component. This is why the normal component actually overdumps all motion of any topological defects present, but doesn't have its own dynamics. It's a nice viscous system in which to study things, just the structures and things. There will be two main types. Well, there are very many different types of vortices, but there will be a skyrmion of that type and a vortex sheet, basically a soliton with a trapped vorticity, another type of vortices I'll be mentioning. On the other hand, if we take very pure helium-4 and cool down to just about 0.5 or 0.3 Kelvin, it's already the zero temperature limit of helium-4, in which there is only one type of topological defects, quantized vortex lines, which are absolutely underdamped at these temperatures. So the dynamics is really the pure dynamics of vortex lines with a huge range of wavelengths, length scales. Right, just again, helium-4. It's the simplest type of superfluid, just a simple scalar complex order parameter, which has 2 degrees of freedom. One soft degree is the phase, which allows quantized circulation. And basically, as we were told, at the superfluid component, which is the only component which is present below 0.5 Kelvin, that's our domain, is absolutely inviscid. But most importantly, it is that the circulation is quantized, so the topology, the circulation around this vortex is always preserved due to topological constraints, well, quantum mechanical constraints. On the other hand, if you take another isotope of helium, helium-3, and cool it down to 2 millikelvin and compress, and without magnetic field, you would obtain a small niche of this interesting A phase. What makes the ordered part of superfluid helium-3? Cooper pairs made of 2 helium-3 quasiparticles, which have a non-zero, P-wave orbital pairing, and also a triplet spin pairing, because they have spin 1/2 each. So both basically become ordered, and the total order parameter of this phase has 6 real degrees of freedom, of which orbitals look like that. I'm not going to dwell on that. Basically, it's a chiral superfluid, not just anisotropic, but chiral, but both orbital degree local director and spin director make some textures in space. They're basically pneumatic liquid crystals, or with in both orbital and spin space. However, in some simplest cases, L and D vectors are coupled due to spin-orbit interaction, and that's our case. And just to show you, I show the simplest functional of free energy expansion in various terms. You can quickly see here the elastic energies of liquid crystals, also anisotropic kinetic energy of superfluids, plus some chiral terms where velocity enters linearly into the energy, and hence actually different senses of rotation produce different signs of contribution to free energy. To constrain this kind of beast a little bit, we confine helium-3 between 2 parallel walls, which enforce simple ground states either always should be normal. Well, either L vector up and L vector down. I will only be talking about the orbital degrees of freedom, which indicate the motion. Yeah, we're not mentioning spins at all. However, there could be domain walls between. Just again, if there are no domain walls and we made just a single domain texture, and here this object is basically the symmetry of the order parameter of the local order parameter, of all information about the three soft modes of the orbital order parameter, the Euler angles of this object can be shown by this sort of traffic cone, like three, well, all different orientation of that would keep all the information about the orbital degrees of freedom. So that's what is shown here. For example, if you take a single domain of L texture and start rotating it in one direction, in our case, there could be various types of quantized vortices, but the one which has lowest energy and also lowest critical velocity for nucleation is this so-called symmetric, so-called continuous vortex or skyrmion. Basically, it's a topologically stable texture, which has two quanta of circulation that way. On the other hand, if you try to rotate in the same direction the oppositely oriented L texture, basically the time reversed L texture, you expect a different type of skyrmion to show, a hyperbolic skyrmion. It has a high energy of its core. It has basically less symmetry, sort of more deformations in it. If you in your sample have two domains of different chirality, there would be a domain wall between them. It can be homogeneous in space, or it can have kinks on it, like kinks between nail walls or block walls in ferromagnetic domain walls. These kinks are also skyrmions or merons. They have quantized circulation in that. So if you basically, that's it. That's a propaganda of what we can do with this system. And experimentally, as we've just published recently, we found that we can create monodomain chiral textures of helium-3A and know which way the L vector points. Actually, we create them by cooling through the TC while rotating, hence actually breaking the degeneracy in space, this chiral. L vector always is being created anti-parallel to the angular velocity of rotation. That's there are various ways to explain that by but it sits in the free energy functional. And when then we try to rotate, if we prepare such a state and then rotate it again in the same direction as we did, these types of skyrmions will enter the system, like here. However, if we try to rotate it backwards, it responds very differently, which is the proof that the system is chiral. And instead of isolated vortices, a vortex sheet is being created and moves in or out depending on whether you accelerate or decelerate. That's just kind of the essence of several years of experimenting. Yeah, I told you. Right, nice. So nice homogeneous systems, isolated vortices. Can we do something with something more complicated? Yes, because if we didn't produce a single domain texture, in principle there are 4 different ground states of this system if there are no bias. L and D vectors each can point either up or down. So 4 combinations, 4 colors shown here. And in principle one can expect if you break symmetry kind of independently in different regions of space, you will get a mosaic of those quasi-two-dimensional mosaic of those domains with 3 possible types of domain walls, 2 of which can carry vorticity. I mean, it's an interesting zoo with lots of algebra kind of what is possible, what is not involved. For example, Y-type and X-type junctions are allowed dependent on angles and types of walls. And we try to simulate them using just a minimization of a slow minimization of the free energy of Ginzburg-Landau type. Basically, we randomly initiated a 2-dimensional matrix of these L and D vectors, and then allow them to coarsen where the only relaxation process, the slowest relaxation process is the orbital viscosity of the L vector, about which Richard Haley was talking yesterday. Basically, by allowing this sort of overdamped coarsening, we've observed, well, similar type of coarsening as many other systems people do observe. And why did we do that? Because we already have lots of information that we have those domain walls. We cannot visualize them yet, but we are working on that. And somehow if they're there, they will stay in our cell forever. They don't get removed completely. We were interested, maybe, as there was proposal, these types of three-way junctions can arrest some metastable kind of frustrated situation of this mosaic. Or maybe it's just pinning due to small roughness of our confining walls. Well, the simulations show that no arrest is happening when we initialize the system randomly. If you do it in a sort of honeycomb type of way, you can actually make an artificial stable structure. But clearly, in real life, we don't expect anything artificial. So the bottom line, everything coarsens as it just does under tension, even though there are trapped vortices and junctions of these walls. Well, that's sort of some way the total length of each of three types of walls change with time, and the exponent is 1/2, which is just a standard scaling of coarsening when you have just single length scale and everything is tension dominated. That's it about helium-3a, a rich system in which we are working. Now let's get back to a simpler system in which there will be turbulence. And it would be a very simple system if there were no kinetic energy of flow, because then it would be just a network of elastic strings. Zero temperature, again, a tangle of quantized vortex lines, whose dynamics is pretty well known, but they can reconnect, and they can interact through mutual polarization. But basically, all information is about the system is if you know the positions of these filaments, you know everything about this system. This is why the filamentary model for helium-4 is, well, believed to be so successful, because the core size of these vortices is just 1 angstrom. All of the rest is just ordered flow according to just simple coherent order parameter. Right. What is important? As I said, all equations of motion are known. It's just the dynamic of this complex system is of interest, because there are some factors. And please just remember, I try to stress this point, that there are two types of energy we will be talking about. One will be called the quantum energy, basically the energy associated with the particular single defect of the kinetic energy of the flow around each of these vortices. It's the line energy of vortices. So that's what makes them different from classical fluids, which don't have quantized vortices. Right. However, if the several vortices are arranged in a bundle, or at least have some mutual alignment, there will be far-field flow around all of them, which can have kinetic energy actually quite larger than that energy due to their quantized nature. So dependent on the type of correlations, you can have either one dominating or the other, and that will be the main point. Basically, very often when people say, we had a tangle, we simulated a vortex tangle and its vortex length was changing like something. Yes, the total vortex length is a very important observable, which just because thanks to these well-defined defects which we can have in the system. But it's by far the only parameter which matters. If you don't know what are the correlations between polarization of vortex lines, you really don't know much. And basically, this parameter L is not conserved. There are no actually any conservation laws about that. But the energy is conserved, and the momentum is conserved, and angular momentum is always conserved in some localities. So these are integrals which actually will change dynamics of these tangles dependent on how you prepare them. Just to tell you what types of situations we often have. Our cell has 5 centimeters on a side, and if we manage to stir a flow on length scale, and the typical density of vortices will be such that the distances between vortices will be of order fraction of millimeter, sometimes even millimeter, which means anything on scale smaller than 1 millimeter or something is already a quantum regime where actually dynamics behavior of individual quantized vortex lines is mostly important. However, if you have some flow on scales larger than that, you can coarse grain this discrete vorticity and forget about it. You recover the classical description if you have that energy dominant. And it is believed that if you store the energy here or there, eventually it will, due to various processes, cascade without dissipation down to some dissipative length scales, helped by reconnections. But eventually it is believed that two processes will take the energy away. Emission of phonons, the shear viscosity is 0, but the second viscosity is none. You can emit sound. But also, if your system is inhomogeneous, reconnections would produce small vortex rings, which can also take the energy away to infinity. Right, so that's methodology. So the classical cascade is, of course, something like a Kolmogorov type of interaction of large-scale eddies or bundles. And quantum cascade might have various different various processes, mainly interaction and reconnections of individual lines or bundles of them, and eventually Kelvin waves. And that's it. Again, just to reiterate, locally the velocity of flow is, of course, should be calculated using the Biot-Savart integral because you have line vorticity with fixed circulation around each of them. But you can take the local field due to the nearest vicinity of your particular vortex. It will be like local induction approximation is often used. But you can, if there is a polarized bundle, you would have also far field velocity. You add them together, square, and that's your energy. But sometimes this dominates, sometimes that dominates, and they have very different structures. Right, and that's what to expect from the free decay of two types of vortex. This would be the simplest mathematically vortex, absolute random vortex tangle. Very hard to prepare experimentally. Because nothing is random in this world, right? But mathematically, if you prepare it, you let it relax, and it will have just one length scale, no large scale energy. All energy sits just in the tension of vortex lines, and it will scale, decay is 1 over t, basically the decay predicted by Joe Winan in his original equations of 1958-ish, well, he knows better, right? And basically the bottom line, the free decay should be like 1 over t, a standard decay of a system with one length scale. Now, on the other hand, if you've stored it mechanically on a large scale and the size of your box is finite, so which means the integral length scale of classical turbulence is fixed in time, then your classical energy, if it's there, will be the slowest process in the system at the largest scale, and everything will decay with, well, again, subject to a couple of, thank you, to other assumptions like T2 minus 3/2. So this is classical, quasi-classical, quantum turbulence, this is random. Right, well, then you can also, if you really want to study correlations in bundles, you can study everything in rotation, and rotating turbulence will be actually more robust against perturbations because there are, angular momentum conservation, something vortices just don't want to reconnect because provided the vorticity, large-scale vorticity is constant. Or you can inject a large-scale vortex ring, which was just told half an hour ago, and well, you can either inject individual vortex rings polarized and they will propagate in a particular way, or they can reconnect and make a polarized tangle localized in space propagating. All these systems can be studied, and we do, and I will study them in this gold-plated cube, right, but with use of ejected electrons, and I'm just about to conclude, which normally sit on quantized vortex rings of 1 micron or 5 micron size, which we use as both probes and drives and all kind of handles to deal with the vortices. And I'll just tell you that if the vorticity is random, we do recover 1/t decay with a particular rate of decay. If the vorticity is quasi-classical, we recover T2 minus 3/2 decay. They produce very different rates of dissipation. The quasi-classical dissipation, this is parameter, rate of energy decay per basically square of vortex lines. Partially polarized lines in bundles decay, decay, the kinetic energy decays 30 times as slowly. Then we can do lots of other things like study the stability of rotating turbulence, blah, blah, blah. And thank you very much. This stuff. Yeah, right.
That's the part I wanted to see. No time for questions, so if Jakob